You guys probably know by now that the development of Newton's laws was a result of 2000 years of trials, errors, and triumph. It started with our understanding that the Earth was round. It ended with the understanding of gravity. Similar developments happened in optics, the study of light. Unfortunately, most physics textbooks, including ours, gloss over that fact. The reason they did that was because that development happened to a great extent in India, the Muslim world, and the late Middle Ages. Recently, we've learned a lot about those developments, and yet these are not in your textbooks, so I'm going to add a little bit of that in the next few minutes. So let me introduce the history of geometrical optics, a topic that originated in the ancient world and which developed until the time of Newton. Yes, Newton contributed to it as well, but interestingly enough, he also messed it up big time. The Greek Euclid, whose work you learned in Geometry 1 and 2 in middle school, is credited with being the first to discuss the properties of light as rays. The fact that light usually moves in straight lines was used by him in developing his Elements. Elements is a book about geometry, and believe it or not, it's the second bestseller of all times, the first being the Bible. Euclid described what it meant to magnify, for example, something we will need to understand when we learn about magnification, lenses, and telescopes. Unfortunately, the Greeks thought light came out of the eye, illuminated objects, and moved at infinite speeds, and that is how we saw. It was not clear whether they meant that the light moved back into the eye, but that was inconsequential since the speed of light, according to the Greeks, was infinite. Here's their proof. When we wake up, we see the stars. These are very far away. The Greeks thought the stars were illuminated pieces of ice on the celestial sphere that surrounded us. Now, if they were illuminated by the sun, and if the sun was eclipsed, for example, by Earth, we would see the stars disappear in a round portion of the sky. And we never do. Not bad, eh? Damn wrong, but not bad. Hero of Alexandria and Ptolemy, the guy that developed the geocentric model most, developed optics a little further. Still, it was a Persian and Iraqi scholar that gave huge boost to the field. That's during the modern golden age of the Muslim culture between the 9th and 13th century. First, it was Ibn Sal in the 10th century that developed optics to a point of usefulness. Using his version of developed Euclidean geometry, you could actually build lenses, fashion them from glass for the first time, and build mirrors, fashion them into reflectors for the first time. Such reflectors, like the one in your car's headlight and later in telescopes, were something that started in the Muslim world. Next came Al-Hazen or Al-Hazen. He combined his mathematical and experimental results. Avicenna, at about the same time, Avicenna or Ibn Sina was the inventor of Newton's first law, believe it or not, in the 11th century. He combined more mathematical results with the results of Al-Hazen, but He also had a brilliant insight that made him see that the speed of light must be finite and that light comes from, surprise, surprise, shining objects like the sun, not from the eye itself. Notice that this result in the understanding of how stars are combined together. Therefore, in a sense, Avicenna was also the father of modern astronomy, in that stars suddenly get a completely different meaning once we say that the speed of light is finite. The Islamic world did not develop as much after its golden age between the 1200s and the Renaissance 200 years later, possibly because of Mongol invaders that killed 70% of all humans in Persia and demolished the best library in the world in Baghdad in 1258, at about the same time that the big library was burnt in Spain due to religious wars, and in present-day Turkey, that was actually part of the Crusades. As the Muslim world science was in decline, Europeans learned ancient Greek astronomy and Arab science from Ibn Rushd of Spain, also called Averroes, some Jewish scholars from Toledo, and Constantine the African, a Muslim Arab that converted to Christianity. The Europeans basically started their big work in optics in the 13th century with a fellow by the name of Robert Grotesette and Roger Bacon. What they did is they came up with a new approach to science, and that is something that later on was used in astronomy as well and in the study of mechanics. Basically, the main thing that they used is this idea that the simplest explanation is the best. That's known now as the Occam's razor. Roger Bacon is known for being the first person to have fashioned proper lenses in the West. In Newton's century, two Dutch scholars, Snell and Huygens, developed an explanation of light that concluded that light was a wave. Newton, however, preferred the view where matter is made of heavier atoms and light of lighter corpuscular particles. Only Newton said that light still moves faster in glass and slower in air and vacuum. Wrong. There was something where Newton was absolutely wrong about. Not too long before Newton, it was Galileo that figured out a way to measure the speed of light, while in Newton's time, somebody eventually did. Here is Galileo's scheme for measuring the speed of light. He sent an assistant to a mountain few tens of miles away. He climbed on another mountain. He then uncovered his lantern. The moment the assistant saw that lantern, he uncovered his own. Galileo measured the time from when he uncovered to when his assistant uncovered the lantern. In a sense, this will be the way by which we, in Physics 3, will measure the speed of light. This method failed. Reason is, light is so fast that your response, which is of order of a tenth of a second, as you may recall from Physics 1, your personal response time is way too long for getting an accurate result on the speed of light this way. Ole Romer from Denmark had a very different way of measuring the speed of light, and that one worked. He took Galileo's measurements of the moons of Jupiter. Galileo discovered 4 moons that orbited Jupiter. We now know of 20, but at the time only 4 were known, and with the small telescope all you can see is 4. Let's concentrate on one of them, the closest, Io. Let's assume that Io orbits Jupiter once in exactly 2 days. It's not exactly right, but for simplicity let's assume that once in every exactly 2 days Io circles Jupiter, which means that once in exactly 2 days Io disappears behind Jupiter. Now, if you wait 6 months, this should be, let's say that you're waiting 180 days, which is almost 6 months. In those 180 days, Io goes 90 times around Jupiter. So you should expect that, let's say for example that Io was disappearing exactly at a certain hour, let's say 9 p.m. taking into account that Earth moved to the other side, and taking that into measuring your time, you should expect that exactly at the same time, we call it celestial time, at exactly the same time Io will disappear. But it ended up that when Earth was on the far side of the Sun from Jupiter, Io disappeared 16 minutes after the time that it was supposed to disappear. That's because light takes, I give you a little time. Yeah, indeed, the light takes 16 minutes more to arrive from Io to Earth. Therefore, the distance between Earth and the Sun, which was known not quite well, but was known fairly well at the time, divide that by 16 minutes and you get the speed of light. Neat. That is what Romer did. His value was a little too slow, 240,000 kilometers per second instead of the almost 300, and that was because we did not know the exact distance between the Earth and the Sun at the time. In 1729, a British astronomer by the name of James Bradley found a nifty way to measure the speed of light independently. This was an independent confirmation on the speed of light. This is called the stellar aberration of light. Nifty idea here. Now, don't try this at home, but if you have a car that's moving at 10 miles per hour and somebody throws an object, let's say a golf ball, through your window at 10 miles per hour, the passenger that didn't know that the car was moving would see a golf ball comes at an angle. That angle will be determined by the ratio of the speed of the golf ball and the car's speed. Think about the golf ball as light and the car speed as earth. In the example I gave, if it's both 10 miles per hour, the angle would be 45 degrees. Another analogy would be, say you're running in the rain with an umbrella and the rain's coming down, but since you're running you have to hold the umbrella at an angle, and that angle, if both are the same, would be again 45 degrees. No such huge degrees are gonna be happening in the case of measuring stars. But the idea is the same. Two situations here. The golf ball, the light, is coming at 90 degrees angle, as in the picture on the right, or it comes from the back, or it comes from the front, as Earth is moving away from that star or towards that star. Which means that as Earth moves at 90 degrees to the incoming light, you would see that star as if it was not exactly straight up, but at a slight angle. James Bradley actually measured that angle and found out that it says that the speed of light is very close to the present day value of 300,000 kilometers per second. The speed of light was measured with higher precision and, of course, as a result, greater accuracy in the 19th century by Fizeau, a French scientist. The idea was the following. A light source reflects from a mirror that's half silvered, so that half of the light goes through and half of the light bounces off, as in the picture below. It goes through a toothed cogwheel and bounces back. As you start spinning the cogwheel faster and faster, you get to a speed at which the light goes through the cogwheel, then bounces back, then hits the cogwheel itself, therefore you see little. Then the speed increases further until you suddenly see a dot. By figuring out the spin rate, you can then figure out the speed of light. That nifty little method is going to be fairly similar to the experiment that you're going to do measuring the speed of light in Physics 3. We have done that experiment in Physics 2, but we will do the same thing to a much greater precision. So that's basically it for geometrical optics and the measurement of the speed of light. Physical optics is the study of how optics is also the study of light as a wave. Beforehand, let's think about Newton's Principia for a few more minutes. Newton himself became famous for his book about optics, in which he described various things, his wrong notions about optics, but also ways by which, for example, to build a reflecting telescope. He became a celebrity among scientists after Principia and actually after his death. That was because the Halley comet came back 76 years later. That comet was discovered by Newton's friend Edmund Halley. Of course, it was a shock to everyone. Basically, gravity and Newton's laws meant that suddenly our universe became huge. Before Newton, the whole of the cosmos was not much larger than the orbit of Saturn around the Earth. That's where the celestial sphere was. After Newton, it became quite obvious that the size of the universe is at least hundreds of thousands of times larger. Suddenly, science became super important. Before the time of Newton, Galileo already asked for scientific independence, basically that science and religion should not mix together, and this was accepted by the Pope in the year 2010. Basically, paradigm shifts take time. Newton published math, physics, and astronomy in Principia, and other fields kept on developing. But the Brits were a bit suspicious of optics, so it took a long time until they accepted basically what should be now regarded as optics. At around Newton's time, Huygens and Snellius of the Netherlands kept asking, if light is traveling, in what is it traveling? Is it traveling in a medium? Both accepted the fact that Newton discovered that planets orbit in empty space between planets. How empty is empty, they asked. The drag, you guys remember drag from Physics 1, the drag could in principle slow down the planets if there was any fluid. So whatever there was between those planets had to be incredibly fluffy. Little mass, no drag. They called it the ether. That very light, fluffy thing that wouldn't slow the planets was called the ether. This idea did not catch on in England until 1802, when an English fellow by the name of Young performed the experiment described on this slide.